students, let us start with example. Prove that intersection of two subspace is a subspace. Prove that intersection of a two subspace is a subspace. In previous video we have discussed what is subspace. Okay. Solution: let H and K be two subspaces of vector space V. I here write short form for vector space V dot S. Let U comma V belongs to H intersection K. Okay. This implies that we know the definition of when we say that H is a subspace if 0 vector is belongs to H. Second is U and V belongs to H, implies U plus V is belongs to H, and third one is K into U is belongs to H. Here obviously H and K are subspaces, so their 0 vector is belongs to H also belongs to K. That's why this 0 vector is also belongs to H intersection K. Now you let U and V belongs to H intersection K. That implies U is belongs to H and not only U comma V belongs to H and U comma V belongs to K. But H and K are subspaces. H and K are subspaces. Therefore, by using definition of subspace, U plus V belongs to H and U plus V belongs to K. That implies U plus V is belongs to H intersection K. Then second property is satisfied. Now third, for vector U belongs to H intersection K. For vector U belongs to H intersection K, C into U belongs to H and C into U belongs to K for some C belongs to R. C into U belongs to H and C into U belongs to K. That implies C into U belongs to H intersection K. This step implies U belongs to H and U belongs to K. In next step, C into U belongs to H and C into U belongs to K, because H and K are subspaces. Therefore, H intersection K is a subspace or intersection of two subspace is always subspace. Okay. Let us take one example for homework. Very simple. Show that union of two subspaces may not be a subspace of vector space. Okay. Now let us see next topic. Null spaces Next topic is null spaces, column spaces, column spaces, and linear transformation, and linear transformation, and linear transformation. Okay. First of all, we see what is null space. Null space definition. Definition of null space. The null space of an m by n matrix. The null space of m by n matrix. The null space of m by n matrix A, written as null space of A, is the set of all solutions. Is the set of all solutions. Is the set of all solutions of the homogeneous equation of the homogeneous equation A into X is equals to 0. Null space of A means what? Set of all solutions of the homogeneous equation A into X is equals to 0. That is, in set notation, null space of A is equals to set of all X such that X is belongs to R n, AX is equals to 0. Okay. This is null space of A. Or we can say that null space of A can be described as the set of all X belongs to Rn are mapped to a 0 vector of Rm. Via linear transformation X to Ax. Okay. Let us write down theorem. The null space of A is a subspace of Rn. The null space of A is a subspace of Rn. The null space of A is a subspace of Rn. Okay. Let us see proof. It is clear that null space of A is a subset of Rn. Obviously, null space of A is a subset of Rn. The zero vector belongs to null space of A by its definition. Let U comma V belongs to null space of A. Therefore, A into U is equals to 0, A into V is equals to 0 by definition of null space. Okay. Now consider A into U plus V is equals to AU plus A into V. U plus V belongs to null space of A means what? A into U plus V is equals to 0. Now A into U is 0, A into V is 0. So this is 0 plus 0 is equals to 0. Therefore, A therefore u plus v is belongs to null space of A. Here we have taken uv belongs to null space of A. We have shown that u plus v is belongs to null space of A. Second property of subspace is satisfied. Now third, let C belongs to R, then A into C into U is equals to, C is a constant, so take outside to the bracket, A into U is equals to C into 0, which is equals to 0. That implies C into U belongs to null space of A. Therefore, null space of A is subspace of Rn. Okay, very simple. In first semester, we have already learned the method of solving homogeneous system. Now we will explicitly describe null space of A for matrix A. Also we determine whether the given vector belongs to null space of A or not. Okay. Let us take one example. Let A is equals to matrix 1 minus 6 4 0 0 0 2 0. For matrix A, we find for matrix A, find null space of A. Find null space of A. Okay. Solution. We have A is equals to matrix 1 minus 6 4 0 0 0 2 0. Okay. Reduce this matrix A into row echelon form. Its row echelon form is, see here, for row echelon form, here actually this matrix is given to you is augmented matrix. So this matrix is equivalent, okay, we have this matrix A. Reduce matrix A to row echelon form. This matrix A, okay, reduce matrix A to row echelon form. Row echelon for 1 minus 6 4 0 0 0 2 0. If here we make 1, so this matrix will be equivalent to 1 minus 6 4 0 0 0 1 0. Okay. Now the given matrix A is in row echelon form with two leading elements x and z, and x and y variable is free variable. Okay, so the given matrix A is in row echelon form with two leading elements x as x and z, say we can can say x1, x2, x3. That doesn't matter. Therefore, from last row we will get z is equals to 0, and first equation x minus 6y plus 4z is equals to 0. That implies x minus 6y is equals to 0. That implies x is equals to 6y. Therefore, the general solution is what is matrix x, y, z, which is equals to x is nothing but 6y. Okay, this is y. Y is a free variable, so y keep as it is, and z is 0. This is equals to y into 610. Suppose this vector is u. So this shows that every linear combination of vector u is an element of null space of A. Therefore, the set U spans null space of A. Therefore, null space of A is equals to span of set U. Means every vector in null space A can be written as linear combination of U. Next, let us take next example. Take this example for homework. Find null space of A where A is equals to matrix 1, 5, minus 4, minus 3, minus 3, 1, 0, 1, minus 2, 1, 0, 0, 0, 0. Okay. This is very simple. This matrix is already in row echelon form. Okay. We have to just solve A into x is equals to 0. Here suppose 4 variable x, y, z. So you will get matrix x, y, z, w. Find these values by using ax is equals to 0, y. We will get minus 6z plus 8w minus t, 2z minus w, z, w, and t. Sorry, here also w. Okay, because here are 5 columns, that's why we will take 5 variables. Okay, now see here, z into minus 6. Write down the coefficient of z. Minus 6, 2, 1, 0. Okay, 1, 0, 0 plus w into 8 minus 1, 0, 1, 0 plus t into minus 1 plus t into minus 1, 0, 0, 0, 1. Okay, this is suppose vector v1, this is vector v2, and this is vector v3. So this can be written as zv1 plus wv2 plus tv3. Okay, so null space of A is nothing but span of V1, V2, V3. Okay. Let us take next definition. Column space. Definition. Okay. Column space of an m by n matrix, column space of an m by n matrix A, written as column space COL, column space of A, is the set of all linear combination of the columns of A. If A is equals to matrix A1, A2 and so on up to AN, then column space of A is equals to set of all A1, A2 and so on up to AN. We know that span of A1, A2 and so on up to AN is a subspace of This is by theorem. Column space of an m by n matrix A, it is written by column space of A, is the set of all linear combination of the columns of A. Okay, that is, if A is equals to, suppose A contains columns A1, A2 and so on up to AN, then column space of A is nothing but equals to span of A1, A2 and so on up to A. Okay, means it is a set of all linear combination of the columns of A. Okay, in next line write down one theorem. The column space of an m by n matrix, the column space of an m by n matrix is a subspace of Rn. Okay, we are not going to see proof of this theorem. Just remember that the column space of an m by n matrix A is a subspace of Rn. Okay, let us take example. Column space of A is what? It is the set of all linear combination of columns of matrix A. Okay, let us take example. Example is find matrix A such that W is equals to set of all matrix B minus C 2B plus C plus D 5C plus 4D, sorry, here is minus D, such that BCD, okay, I will write down. W is equals to set of all matrix B minus C 2B plus C plus D 5C minus 4D D, such that B comma C comma D belongs to R, set of real number, which is equals to column space of A. We have to find matrix A. Given condition is W is equals to set of all these matrix such that BCD belongs to set of all real numbers, which is equals to column space of A. Okay. We have to find matrix A such that W is equals to column space of A. Okay. In W, matrix is of the form B sorry 2B plus C plus D, 5C minus 4D and D. Okay. This can be written as B into, write down the coefficient of B, 1, 2, 0, 0. Okay. Plus C into minus 1, 1, 5, 0. Okay. Plus D into matrix 0, 1, minus 4, 1. Okay. Therefore, we get W is equals to B into 1, 2, 0, 0 plus C into minus 1, 1, 5, 0 plus D into 0, 1, minus 4, 1 such that B comma C comma D belongs to R. Suppose this is A1, this is A2 and this is A3. So we can write W is equals to span of which vector? A1, A2 and A3. W is the set of all linear combination of A1, A2 and A3. Therefore, and this W is nothing but columns of matrix A. Therefore, required matrix is the required matrix A is equals to matrix 1 minus 1 0 2 1 1 0 5 0 5 minus 4 0 0 1, which is equals to matrix A1 A2 A3. Okay. This is the matrix A. Okay. Let us take next example. Let A is equals to matrix minus 8 minus 2 minus 9 6 4 8 4 0 4. W is equals to matrix 2 1 minus 2 for given A and W. Determine whether W is in column space A. Determine whether W is in column space of A in null space of A. We have given matrix A and one vector W. For this A and W, we have to determine whether W is in column space A or in null space of A. Okay. solution. To check W is belongs to check W is belongs to column space of A, solve the system. We solve the system AX is equals to W. Solve the system AX is equals to W. So write matrix A, X is equals to vector x1, x2, x3 and W is equals to W. I will directly write here augmented matrix. You have to find out this augmented matrix. Augmented matrix is matrix -8, -2, 9, 2, 6, 4, 8, 1, 4, 0, 4, -2. Oh, sorry, this. Okay, this is augmented matrix. We have to reduce to row echelon form. Reduce to it reduces to row echelon form. Reduces to row echelon form as obtain this row echelon form. This is homework to you. 404 - 204 2. Okay. Observe here. Third and fourth columns has no leading one. That's why this system has a infinitely many solutions. Therefore, this system is a consistent. From the above form of augmented matrix, or from this matrix, it is clear that the system AX is equals to W has infinitely many solutions. That's why it is consistent. Therefore, vector V can be written as linear combination of columns of A. Therefore, W is written as linear combination of columns of A, columns of A. Therefore, W is belongs to column space of A. I will take here one table which describes the contrast between null space of A and column space of A. Null space of A and column space of A. Null space of A is what? It is the set of all. It is the set of all solutions to the matrix equation X is equals to 0. And it is the set of all column space of A is what? Set of all linear combination of columns of A. Okay. Null space of A is a subspace of Rn. If you have taken matrix of size m by n, then null space of A is a subspace of Rn and column space is a subspace of Rn. Null space is a subspace of Rn and column space is a subspace of. If V belongs to null space of A, then A into V is equals to 0. Let V belongs to column space of A, then A into X is equals to 0. Then A into X is equals to, then the matrix equation A into X is equals to V is consistent. Null space of A is equals to singleton 0 if and only if the linear transformation x to ax is 1 to 1 and column space of A is equals to Rm if the linear transformation x to ax maps Rn onto Rm